Okay, so you have probably seen your midterm, the first midterm grades. I mean, I just scanned your papers. I will send them to each one of you by email, so you will all get a chance to see all of them. And you can spend as much time as you like with your paper. And now we need to decide about the date of our second midterm. I mean, I think we should better have it next week. We can have it either, I mean, this is next week's calendar. And we can have it on Wednesday again. We start in the lecture hour, and we will have time until 5. Or another possibility is to have it on Saturday.
After Wednesday or before?
After Wednesday. I mean, I would rather give you at least 1 week notice before the midterm. So the earliest we will have next Monday. One possibility would be to have it on Saturday.
And maybe we have 105 exams.
That is this weekend. It is this weekend. Everything until the day of the exam. Everything starting from the first lecture up to everything we covered the day before the exam, let's say.
I think Saturday is okay. After this information.
The later it is, the better it is.
Because we have 105 on Thursday.
This Saturday.
Yes.
So at what time should we start? I mean, one possibility might be we can start at, I don't know, around 9 or 9:30, and then continue until you get hungry. No, I mean, I'm not against that. But I mean, you get hungry.
Because sometimes when there's traffic, it's 8.
Take the metro. There's no traffic there. Well, just keep this in mind. I mean, you have something like 3 hours where you can find new ideas about how to solve the questions. So after 3 hours, you get tired, no new ideas will come to you. So if we start around 9, let's say, we can continue. I mean, you can effectively work on the questions until 12, and then you'll start getting hungry. I mean, you see, I will not just grab the paper from you. No matter at which time we start, I mean, as long as you continue writing your solutions, I will just let you keep your paper. I mean, you can order, I mean, you can bring your food, your drinks, etc.
So if we're going to be effective only for 3 hours, why should we start super early? I mean, 10:30 seems nice.
Well,
1:30 and then
10:30, I already start to get hungry for my lunch. Yeah, I mean, if you prefer 10:30, that's fine. But, I mean, come on. I mean, it's Saturday. If you start at 10:30, then you probably will quit around 1 or 2. Half of the day is already gone. Let's do it Saturday at 10. I mean, if you come a bit early, I will probably be here a bit early. If you come a bit early, I will just give you the paper and you can start. you will have 3+ hours. So you can just sit there if you like for 3 hours. After the third hour, I will just ask you to finish the question you are solving. And don't start to think to come up with a solution of a new problem. Okay. So it is the Saturday 14th. Okay, in the first midterm, so that you won't make the same mistake in the second midterm, if you remember, there was one question, which was the energy was given by C times P to the power SC, and S being constant, or I think it was N. Some of you just took N is equal to 2 and solved the question with N is equal to 2. You lost most of your points. I mean, N is equal to 2 case is what we had already studied in the book. I mean, with a cheat sheet, you have already all the formulas necessary, so it doesn't really make too much sense.
Are we going to bring a cheat sheet again?
Sure. I mean, just bring your cheat sheet. If you think you have forgotten any formulas, then let me know, and I will write it on the board. Other questions?
For the makeup exams, the makeup exam will be before the final exam?
If there will be a makeup exam, it will be after the final. So I usually do a makeup exam under 2 conditions. If you have a medical reason for not attending the exam, or for example, it happens sometimes that you have 3 exams and 2 of them are really high, 1 of them is just very low. Then I also let you enter the makeup exam. Then it's obvious that there was something on that date that you couldn't show your performance. So I also take you for a makeup. But if there are no such cases, I don't give a makeup. So if your grades, I don't know, let's say they are 50, 60, 65, then I mean, there's no variation. If I give you a makeup, you will probably take the same grade. So there's no point for letting you take the makeup. And about the topics covered in the midterm, you might have already realized that, for example, in your homework, if there are 3 questions, 1 of them are always from the first few chapters. So in the midterm also, you will probably get some questions from the first few chapters. Okay, so before starting the discussion, I don't know if you have realized in the material of this chapter, let's say if we go back in our previous chapters, we defined the partition function, which was sum over all the microstates of e to power minus beta epsilon, whatever your microstate is, the energy of that microstate. And what was the energy of the microstate? It was just a sum, so that we wrote this Q for n particles, and if you just make this identification, there is 1 over n factorial. Qn was just assuming the particles are not interacting, 1 over n factorial, Q1 to the n. Now what is this I? Okay, we wrote a sum over I, but what was that I? What does it stand for? What are we summing over? the particles. So we are kind of saying that, okay, this particle has this energy, that particle has the other energy, this third particle has this energy, etc. So that was what we were actually doing there when we were writing this summation. So we were assigning energies or states to individual particles, and then we added that 1 over n factorial prefactor by using the reasoning that if we exchange these particles, the states of these particles, there is no new state created. It corresponds to exactly the same state. So since we are just multiply counting the same microstate, to get rid of that multiple counting, we divide it by 1 over n factorial.
So we're saying that no two particles can have the same energy level?
Sure. I mean, there also there was nothing that prevented it.
If nothing is preventing that, so why are we when we summed over I, why didn't we say that we're summing over levels? We said we're summing over particles. And why do we keep calling it single particle state instead of single energy level state when we're discounting?
Well, let's see. Epsilon 1, for example, in that summation can be equal to epsilon 3. The first particle and the third particle can be in the same single particle microstate. There is nothing that prevents that in that summation. But you see, this combination, you see, if first particle and the third particle are in the same state, even if I exchange them, it's still the same state. If first particle and third particle are in different microstates, if I exchange them, it looks like a different microstate, but if the particles are indistinguishable, they have to be treated as the same microstate. So these two cases were if you compare these two cases, you see a problem with this 1 over n factorial. You see, 1 over n factorial already assumes that by exchanging two particles, you obtain a different looking microstate. So that just consider any ordering of them, and they will actually correspond to the same microstate. So we divide by 1 over n factorial. For if epsilon 1 is equal to epsilon 3 and no other particles are in the same single particle microstate, then we should divide by 1 over n minus 1 factorial, because exchanging n minus 1 of them will give me a different looking microstate, although I have to take them as the same microstate. Okay, that was a problem with that 1 over n factorial resolution of the Gibbs paradox. But in this case, in the grand canonical ensemble, in fact, what we are actually doing is we are writing E as Ni epsilon I, and summing over, let's say, I. So this is the particle index. Now, what is this I over here? Energy cells, or in fact, you can also say as the single particle states. Actually, if you have the energy cells, you can have Gi over here. You see, this will be an important distinction, because here I am not assigning which state a single particle is in. So I'm specifying, you see, in our earlier treatments, we assigned N1, N2, N3. These are the, no, let me not use N, alpha maybe. These are the, if you like, the quantum numbers of particles. So we specify the state of each particle one by one. And then to get rid of this multiple counting, if the particles are indistinguishable, we divide it by 1 over n factorial, which provided us an approximate solution for this multiple counting problem. But here we are specifying so this is a microstate. This was a microstate. in our previous treatment. Now here, these numbers and i's, that is how I define my microstate. So if I use these numbers to specify my microstate, then I'm not really specifying which state each particle is in. So there is no question of exchange. So there won't be any other n factorials, etc. And this treatment will be exact. Exact in the sense that this treatment will take into account the indistinguishability of my particles exactly. Whereas that 1 over n factorial treatment was just an approximate solution for the counting of indistinguishable particles. Now, also, when you are studying, pay attention to a couple of sums we have. Okay, we have sum over microstates of the system. Sum we have a sum over the energies of the system. These are different sums. Then we have sum over single particle states and then we have sum over energies of single particle states. These are all different sums. When we are writing the partition function, here this is a sum over the energies and the total number of particles of the all of the system. When we are writing E is equal to epsilon I and I, this sum over here is over the single particle states. And then we can convert this into and let's say E if we multiply by the density of states for a given energy. And here, GE, the density of states, we will have the density of states for the whole system, n particle density of states, and we will also have the single particle density of states. This energy over here can also be written as sum over the epsilon, G epsilon, and epsilon, epsilon. Here, this G epsilon is the single particle density of states. This is the n particle density of states. So when you see a density of states or a sum, just pay attention to what kind of sum it is, what kind of density of states it is.
For a specific, I'm talking about the n particle density states.
Mhm.
For a specific n, and imagine a group of states, and all of them have the same energy. Is it correct?
What is your system? Give me a concrete system. The reason why I'm asking this is this one. You can talk about as your system, let's say, particle in this, all the particles in this box. Okay, so it's a volume V. Then you have you can talk about the n particle partition function, which will be e to the power minus beta e, and this e will be just sum over I epsilon I. Let me write it not as a sum over each particle, but let me just write it as a sum over the single particle states. So in the ith single particle state, I have ni particles. And then here I'm summing over all the microstates, which will mean that I'm summing over all possible numbers ni of e to the power minus beta epsilon I to the power ni, with the condition that when I sum over all the states in different, all the number of particles in each single particle state, the sum should give me the total number of particles. You see here, each one of these particles can have a different state, can have a different energy. I have n particles, they can all be in different energy states. There is no such constraint. And then if you want the grand canonical partition function, this will be just z to the power n q n sum over all n from 0 to infinity. Yes, for a particular term in this summation, each one of these n particles can have a different energy. This is one way of looking at this problem. Or if I can say that my system is not all these particles in this volume V. You see, when we are defining our system, in fact, we have lots of freedom in our definition of the system. And no matter how we define our system, our treatments will still be valid. You see, we had already seen one of them, one of our freedom, when we were discussing negative temperatures. We said that, okay, the spin of the nucleus of the atoms, I can consider all of those spins as part of my my system and the rest. So I can even separate different degrees of freedom of the same particle and just treat some of them as my system. And then we said that my system interacts weakly with the environment, the rest, and hence we could define a temperature for my system, which was the spins of the nuclei, which could be negative. Here I also have a similar degree of freedom. Okay, I have my particles in my volume V, but I define my system as the particles in the single particle state R, let's say. I pick one single particle state and I define my system as, well, all the particles in that single particle state. What's the number? I don't know. The number is changing. That's why we are using the grand canonical ensemble. The number is not fixed. But what is fixed is the chemical potential is fixed, the temperature is fixed. And then if I want to define the n particle partition function for this system, it will be just e to the power minus beta n times epsilon r. In fact, there is no summation. The summation contains a single term. I have n particles all in the same single particle state. because that is how I define my system. So if for a particular n in this definition, in this system, in this particular system, for a particular value of n, all the particles have the same energy. Then we can go, this is just e to power minus beta n epsilon r. The grand canonical partition function is sum over n from 0 to infinity z times e to power minus beta epsilon r to the power n, which is, okay, sorry. Let me just say n0 or n infinity. N infinity is equal to 1 for fermions and infinity for bosons. And then here, this Q is equal to 1 plus Z e to power minus beta epsilon r for fermions, because n infinity is 1, or 1 over 1 minus Z e to power minus beta epsilon r for bosons, because n infinity is infinite. And from this treatment, if you calculate the average number of particles, you will get the either Fermi-Dirac distribution or the Bose-Einstein distribution. So if you ask me if each one of these particles have the same energy or not, well, it depends what your system is.
It will be unrelated, but why would you want to define a system whose particles are all in the same state?
Well, I mean, does it serve your purpose? What would you like to study? If you ask me to if you are interested in studying the number of particles in a given microstate, then I should better define my system as the particles that are in that state only. Or I can obtain, in fact, the same treatment using the general treatment. Then I will convert every summation to a summation over each single particle states. If I convert this to each single particle state, and from that summation, from each one of the terms in that summation, I can identify the number of particles in that state. So essentially, these are things that you can do if it will serve your purpose. For example, your book quite often, I mean, in this to derive these number of particles, I mean, it uses the micro canonical ensemble, and grand canonical ensemble. So if you do it correctly, you can use whichever ensemble you like. And all should give you the same answer. But you also see the difficulties. For example, to obtain these distributions in the microcanonical ensemble will be much more difficult than to obtain them in the grand canonical ensemble. You see here, just to take the logarithm of this q and take the derivative with respect to z, you are done. You know you already find the Fermi-Dirac and Bose-Einstein distribution. In half a page, you have your answer. If you want to do it in the microcanonical ensemble, I don't even remember how you do it now. You can do it, it is possible, but it will be much more complicated. You see already here in the canonical ensemble, you see here. Just consider that sum of non-interacting particles. It will be complicated because of this constraint. So the sum of each term ni, let's say the sum over n1 will depend on n0, n2, n3, etc. But here, when you go to the grand canonical ensemble, since you are also summing over all possible values of capital N, the total number of particles, it is as if you are summing over each one of those ni's independent of the other one. That's kind of the idea of going to the grand canonical ensemble. The summation over the occupation numbers become independent of each other.
In the last section, there was a container and it was open in the wall.
Mm-hmm.
And just by releasing.
Yeah, before going to the last section, do you have other questions about the earlier sections? So what was the Fermi-Dirac distribution? Plus 1. The Bose-Einstein. And then there is the Maxwell-Boltzmann. No. Yeah, 0, that coefficient is 0. Yeah. Any questions on these? Come on, in your pre-reports, a couple of you had the same question. Under which condition do these three distributions become indistinguishable? They become the same. Under which limit? Yeah. Not 0. They become equal. If e to power beta epsilon minus mu is much, much larger than 1. So if this is the case, then you can just ignore that plus 1 or minus 1. So all of the distributions will be identical. Now that is essentially the classical limit. And can you put a condition on beta from this expression?
It must be high temperature.
Well, let's say high temperature limit. High temperature means beta goes to 0. If beta goes to 0, this exponential goes to e to beta epsilon minus mu goes to, let me put a question mark, 1. What about the low temperature limit? What happens to beta in the low temperature limit? Beta goes to infinity. E to power beta epsilon minus mu.
It's different from distribution.
Depends on the energy. Where is it going?
Well, just give me the conditions. How does it depend on the energy?
Differentiated among each from distribution to distribution.
Okay.
I don't remember exactly, but in one of the distribution, it goes to infinity when the energy is equal to chemical potential. And
Well, you see.
in the bosons,
Well, let's look at this expression. When energy is equal to the chemical potential, let's say in the Bose-Einstein distribution, when epsilon is equal to mu, this is 0, 1 over 1 minus 1, that diverges. Here, this again is 1, is just 1 over 2, finite. Here is just 1. So 1 over 2, 1, infinite. 1 over 2, 1, and, oh, sorry. 1 over 2, 1, and infinite. Right? It seems as if.
Is there any reason to stop us when T is high? Is there any reason to stop us from saying that E should equal 3 over 2 kT in that case?
Is it true? That will be one thing we will be studying. Is E equal to 3 over 2 kT? Because that is a result we obtain from our earlier treatment, where we know that we have not taken into account the indistinguishability of the particles exactly. In fact, we know that it cannot be true at low temperatures. E cannot be equal to 3 over 2 and kT.
But we're talking about high temperatures now.
Hmm?
Now we're considering high temperatures.
Okay, so let's finish this discussion first before going into the U is equal to 3 over 2 kT. What would you naively say as beta goes to infinity? What happens to this exponential?
If the exponent is negative, it goes to 0. If the exponent is positive,
Okay, it goes to 0 if epsilon is less than mu, and infinity if epsilon becomes larger than mu. Okay. What is mu? You see, one question was, okay, you see, if you look at this one, we said that the classical limit, the Maxwell-Boltzmann limit, would correspond to this exponent being much, much larger than 1. And naively looking at these limits, we see that that limit can be achieved, it seems, only if in the low temperature limit. You see, here we have, it goes to infinity. But we had always been thinking that classical limit will be the correspond to the high temperature limit, not the low temperature limit. So what is it that we are doing wrong here?
Mu should be a function of T.
Yep, that's the problem. I mean, we cannot just take this limit as if mu doesn't depend on t. What can you say about the sign of mu? Do you expect the mu to be positive, negative, 0? Or can't you say anything about the mu?
I think it should depend on what type of particle.
How do you determine mu? What is the condition that allows you to determine the value of mu in terms of other variables?
Mu as a derivative of the free energy.
Okay, that is one definition. But you see, let's say, assuming I have my system, you see here I had already in fact mentioned my system. I have a V, I have a closed system, which has a finite volume V, a given temperature T, and I set mu as my variable. But I could have just as well chosen N as my variable. So I have V, N, and T as my variables. You see, when we are writing the equation of state for the ideal gas, there is no mu appearing over there. Everything is P, V, N, and T. Because they are easy to measure. How do I determine mu in terms of these other parameters like V, N, and T? What is the equation that tells me what the value of mu is as a function of N, V, and T?
We can go back to that G equals mu, the average of N, and then we can say that dG in that case what is equal to, and we know dG what is equal to, so we just take care of mutual terms, and we are left with d mu equal whatever is happening.
No. Okay, that might give you a d mu, but d mu will probably be a function of mu itself. You have to integrate. There is an easier expression. You see, if you remember, why did we introduce the parameter mu in the ensemble theory?
To fix the number of particles.
To fix the number of particles. So what's the number of particles? Sum over single particle states n. And n is a function of the energy of the single particle states, beta or T, and mu. So this equation, in fact, will allow me to express mu as a function of T, V, and N. In fact, it will be a function of N over V. Now, this is how I will determine mu. But let's see, what can you say about the value of n? Now, we will study in future chapters, future sections. N is the number of particles. In a realistic system, the number of particles in a given microstate will be a finite number. So that is one condition we have. N should be a finite number. Occupation number should be finite. Well, let's look at the distributions we have. If you look at the Bose-Einstein distribution, for it to be finite, you see, if you have a thermodynamic system, the energy, the single particle energies will almost be continuous. Epsilon will change continuously from the ground state energy up to infinity. But then we know that e to the power beta epsilon minus mu as a function of epsilon, it's an increasing function. But it should never be equal to 1. So e to the power beta times epsilon minus mu should never be 1. So epsilon should never be equal to mu for the occupation number to be finite. You see, for bosons, 1 over e to power beta epsilon minus mu minus 1. This should be always less than infinity. It should be some finite number. But this tells me that e to power beta epsilon minus mu is never equal to 1, which also tells me that epsilon should never be equal to mu. Or, let me write it the other way around, mu should never be equal to epsilon for any single particle energy.
What about the situation when beta goes to infinity and
Let's see. But this tells me that mu, you see, epsilon takes almost continuous values from the ground state energy up to infinity. I can just fix the ground state energy to be 0. So epsilon can take values continuously from 0 to infinity. But that tells me that mu should be less than 0. Mu is negative. For bosons. For fermions, well, that minus 1 is plus 1. E to power beta is always a positive number. Whatever the value of mu, epsilon, and beta is always positive. So there's no such problem. There's no such constraint for bosons, for fermions, sorry. But for bosons, the chemical potential has to be less than 0. Now, to answer your question, how does mu change as a function of temperature? You see, when we were considering these limits over here in the high temperature limit, as beta goes to 0, we were assuming that beta mu also goes to 0. Do we know that? If, for example, as beta goes to 0, mu also becomes very large, then even though beta goes to 0, I can have that exponent to be much larger than 1. That I don't know yet. I have to study how mu changes. You see, there's a minus sign which is kind of deceiving. E to power minus beta mu is not a number less than 1, it's a number larger than 1. So if as beta goes to 0, if mu diverges, then it can still be much, much larger than 1. But to say that, we need to know how mu changes as a function of beta. How can I determine how mu changes as a function of beta? Okay, so let me just, how do you calculate the free energy? In the canonical ensemble or the grand canonical ensemble? Because in the grand canonical ensemble, mu is a parameter. There is no number of particles. If you are talking about taking the derivative with respect to the number of particles to obtain a mu, then you are either talking about the microcanonical ensemble or the canonical ensemble. You see, in the microcanonical ensemble, what were our parameters? Free parameters. N, V, E. Or U. Sometimes we use the E, sometimes we use U. In the canonical ensemble, What were the parameters we have? N, V, T. Here we had we started with the entropy. The derivative of entropy with respect to U was 1 over T. The derivative of entropy with respect to V at constant U and V, U and N, this was P over T. And derivative of the entropy with respect to N at constant U and V, this was equal to minus mu over T. So if we have the entropy, we can find the chemical potential. Now in the canonical ensemble, what were the equations we had? How could we, okay. So what are the equations we have? What is the energy? Here our potential from which we derived all the rest was the free energy, which was E minus Ts. And derivative of A with respect to T at constant N and V, this was equal to minus S. And derivative of A with respect to V at constant T and N, minus P. And the derivative of A with respect to N at constant T and V, this was mu. So again, if you know A, you can determine mu. And then we had the canonical, grand canonical ensemble. We had the Q potential. No, what was the potential in this case? Well, let me just use this one, minus KT logarithm of the grand canonical partition function. Our variables, what are the free variables we have? Mu, V, and T. And this derivative of phi with respect to mu at constant V and T, this was equal to N minus N, etc. Now, if we are using the grand canonical ensemble, we cannot take the derivative with respect to N. So we cannot obtain mu, and we cannot, that strategy will not work. Then you can say, okay, maybe we can use the microcanonical or the canonical ensemble. But then the question is, how do you treat the indistinguishability of the particles exactly in the microcanonical or the canonical ensemble? It is doable. It's not impossible, but it will be complicated. In fact, that was one of the reasons why we moved to the grand canonical ensemble, to be able to take into account exactly the identical property, indistinguishability of the particles we have. So I cannot take the derivative with respect to N and obtain mu. How can I obtain, at least for the non-interacting systems, you see, I have a non-interacting system of particles. How can I obtain the derivative of chemical potential as a function of temperature? Let's say at constant N and V. What is this equal to?
I still believe that what I suggested at the beginning could be done. Would give you this would be minus S over N.
Minus S over N. How do you know?
If we use the Gibbs energy like I suggested in the beginning, we would not have to go through any kind of ensemble.
Okay, guide me through.
Okay, G is equal mu N.
Do you agree? What is G?
G is
No. Yeah.
plus PV.
Plus PV, right?
Plus PV.
Mm-hmm.
But in that
Hmm?
plus
d mu?
n. D mu times n plus dn times mu. If I
Okay, we know that d mu is minus s dt plus v dp. Okay,
So in that case, d mu, how does d mu change with temperature if the pressure is constant?
but you see, this is what I'm interested in. How mu changes as a function of temperature at constant n and v. So d mu by dt at constant n and v will be minus s plus v dp by dt at constant n and v. But we can already say something about the sign probably. Entropy is a positive quantity. So minus s is a negative quantity. This is positive. It's the volume per unit mole. How does the pressure changes as a function of temperature? It should increase. That's what we would naively expect, at least, at constant v and constant n. That's positive. The first term is negative, the second term is positive, so I cannot really say anything about this derivative, the sign of this derivative. That won't be enough. This is still correct, this expression, but this won't really tell me much. Another way of going through any question, in fact, is look at the definition. What was the definition of, how did we define the chemical potential? Well, this was our definition of the chemical potential. 1 over e to the power beta epsilon minus mu plus A. Well, fine. Let's take the derivative with respect to temperature at constant n and v. The left-hand side will be 0. We are not changing n, we are not changing v, so the summation will not change. The single particle energies epsilon will not change as we are changing the temperature. So beta will change as a function of temperature, and mu will change as a function of temperature. So when we are taking the derivative over here, we have to take the derivative with respect to both beta through the temperature dependence through beta and also mu. And this will give us some expression for mu, whether it will be positive or negative. Let's try to go through another argument. You see, whatever your function is, whether you do the Fermi-Dirac or the Bose-Einstein distribution, your function looks like this as a function of epsilon. This is 1 over e to the power beta epsilon minus mu plus 1 plus A. A can be plus 1 minus 1 or 0. And what else we know? We know that the sum of all of these, this gives me the total number of particles. Now, for a given value of epsilon and for a given value of mu, let's say mu is somewhere over here. Okay, let's look at the Fermi-Dirac case first. In the case of the Fermi-Dirac case, it might be that mu can be positive or negative, we don't know. Let's say if mu is positive, let's put it somewhere over here. For a given value of epsilon, if epsilon is larger than mu, then epsilon minus mu is positive. what happens if I draw, here, at this value, what happens to the value of 1 over e to power beta epsilon minus mu as I, let's say, increase the temperature? Beta becomes smaller. Epsilon minus mu is a positive number. So beta times epsilon minus mu as a positive number becomes smaller. Exponential of beta times e to power minus mu becomes smaller. So this numerator becomes smaller. So the number increases as I increase the temperature. I'm not changing epsilon, I'm not changing mu. So what will happen is this value is shifted to here. Let's say. If epsilon is equal to mu, well, nothing will change, it will just stay there. If epsilon is less than mu, let's say somewhere over here, it will just go slightly down. So the new function will have this form. Something like this. You see, this is a red is, let's say this is at T, black is at temperature T, red is at temperature T prime, which was larger than T. Now this is what we would expect. We are increasing the temperature, there will be more particles having larger energy. Right? So this would be what we would expect the number of particles at higher energies should get higher. Now let's see. Okay, so here the number increased for energies larger than mu, but there are already not so many particles over there. But for energy values smaller than mu, the number decreased. And keep in mind, the number we have to keep fixed, the total number. So, not changing mu, we cannot really keep the number fixed. We have to move mu a bit. In which direction should we move mu? To the left or to the right? You see, the question is this one. We have that function. And we are changing, we are increasing the temperature. So if we don't change mu, that black curve, if we increase the temperature, becomes the red curve. But keep in mind that we are summing over all these distributions and the total should be fixed. Now, in this case at least, it's not so very trivial to see, but you see what's happening over there. When we are summing over all these microstates, we are basically integrating over epsilon, multiplying with the density of states, etc. But we are integrating over epsilon. Now, what happened? The number of particles having large energies increased. The number of particles having smaller energies decreased. But most of them already had small energy. If temperature is very small, for example, most of them already had very small energy. So the left-hand side of mu is, the dominant contribution comes from the left-hand side of mu. And that has decreased. But the total number we have to keep fixed. So we have to increase somehow the total number. How can I do that? By changing mu. Should I decrease mu or increase mu? Well, if I decrease mu, for more energies the number will increase. So that would tell me, at least naively, that as T increases, mu should decrease. Well, it will be more clear in the case of Bose-Einstein distribution. Let's look at the Bose-Einstein distribution for the same plot. Now, first of all, we already said that mu should be negative for the distribution to be finite at every value of epsilon. So let's say mu is somewhere over here. This is my mu. So my function, my distribution as a function of temperature, as a function of energy, looks something like this. This is epsilon. So it diverges at epsilon is equal to mu. Now again, I increase T, which means I am decreasing beta. And keep in mind that epsilon minus mu is positive for all values of epsilon. So beta times epsilon minus mu is decreasing. E to the power beta epsilon minus mu is, that value is decreasing. But that tells me that 1 over e to the power beta epsilon minus mu minus 1 is increasing for fixed epsilon and mu. Do you agree up to here? Now, my distribution is increasing. If I don't change anything, if I don't change mu, my new distribution will look like this one. All the occupation numbers increased. But keep in mind, the total number should be fixed. So at certain regions, the distribution should get below its initial value. Well, the only way to make sure that it gets below the initial value is if I make a distribution, okay, at large energies it might have the same value, but at small energies it should go below. But if it goes below, well, it cannot diverge at epsilon is equal to mu, it should diverge at somewhere else. So that blue line should be my new distribution at higher temperatures if the total number is fixed. That essentially tells me that mu drops as T increases, so that I keep the total number fixed.
Why do you want to keep the total number fixed?
Depends on your system. You see, what eventually we will be studying is quantum gas, let's say. I put n helium atoms in a container with a fixed volume V. How does it behave as I change its temperature? The number is fixed, the number will not change. If I can use the microcanonical ensemble, that would be great. But in the microcanonical ensemble, treating this indistinguishability is a mess. So what we do is we use the grand canonical ensemble, where we can exactly treat the indistinguishability of the particles. But in the grand canonical ensemble, I don't have the total number. I'm not fixing the total number. I only have the chemical potential. And I can determine the chemical potential such that my system will have n particles. So then the question is, if I change the temperature of my system, how does the chemical potential of my system change? Keep in mind, the number of particles is the same. It's not changing.
Would it be
Well, you see, for the photons, the number is not conserved. In the case of the helium atoms, helium-4, the number of helium-4 atoms in a container will be conserved. It will not change. So I can impose this constraint. The total number of particles is equal to n, which is fixed. But for photons, the total number will not be fixed. So I cannot impose this constraint. Since I cannot introduce this constraint, keep in mind, at least in the ensemble theory, we introduce mu to keep the number of particles fixed. But if the number of particles is not fixed, then we don't need to introduce mu. So which essentially tells me that mu is equal to 0 for photons. So let's see. Let's go back to our initial question. Let's not forget what the purpose of this discussion was. We were looking at the low temperature, we were considering the low temperature and the high temperature limits, and in a couple of prayer reports it was asked, okay, the high temperature limit goes to beta goes to 0. No, the low temperature limit is when beta goes to infinity, and it seems that all the distributions should overlap in this limit. But now we see why it doesn't work. Why in the high temperature limit we have that condition. Let's see. How does mu change as a function of temperature? Mu is a function of temperature, let's say for bosons. We already said that as temperature increases, mu should drop. Second thing we know is that as mu is negative for bosons, so this is how the chemical potential behaves. It's not necessarily a line, but it's just a function that has a negative, that decreases as you increase T. So you see, as T increases, e to power beta, epsilon minus mu. As T increases, beta goes to 0, but epsilon minus mu also increases. Mu is negative. Epsilon minus mu is always larger than epsilon. And mu is increasing in absolute value as you increase the temperature. So as you increase beta, this doesn't go to 1. It becomes a very large number. So this is the classical limit we have. Now what happens as T drops? As T drops, mu should increase. As temperature gets smaller, mu increases. Well, there are various possibilities. It might never reach 0. That is one possibility. Well, we will see that it doesn't happen. Mu, in the worst case, when T is equal to 0, mu is also 0. It might reach 0 before T is equal to 0. Let's say this is mu C. And this is Tc, sorry. Tc might be 0, or Tc might be larger than 0. That is to be studied in more detail. This is what we call the Bose-Einstein condensate, if Tc is larger than 0. Any questions before we go for a break? In fact, our next discussions will be mainly about how to calculate mu as a function of temperature, both in the classical limit. You see, we said that, okay, at large t, we should recover the classical limit, the Maxwell-Boltzmann. We will recover the Maxwell-Boltzmann distribution, fine. But at large, but not so large values of t, how will we approach the Maxwell-Boltzmann distribution? What will be the modifications to the ideal gas law? And then we will also look at the other extreme. What happens when they are very cold? Then we should see some deviations from the we should see significant deviation from the Maxwell-Boltzmann distribution. One thing was, as you have pointed out, you see, U is equal to 3/2 nkt violates third law of thermodynamics. Okay, let's give a 10-minute break, and then we will see how come this U is equal to 3/2 nkt violate the third law of thermodynamics.